Hello everyone. So in this video, what I want to do is go over several problems that will be similar to what you'll see on your lab exam. So your lab exam will be on My Open Math, that particular platform, and I'll give you guys the instructions on how to sign up for that in Brightspace soon. So in this video, I'm just going to do some examples, some problems that will be similar to those that you'll see. So the first one is you want to make sure you know how to compute percent experimental error. So let's say you're given an experimental value of a density. Let's say it equals 4.55 grams per centimeter cubed. And then you're given an accepted value for density. So that's like your accepted, predicted, gold standard value. Let's say that's 4.47 grams per centimeters cubed. So if you want to calculate the percent experimental error, remember what you do is you take your experimental value minus the accepted value, absolute value of that, so you just make it positive, divide by the accepted value. That's important. So in the denominator is going to be accepted value, and then times 100. So in this case, it would be 4.55 minus 4.47 divided by 4.47 times 100, and that equals 1.79%. Okay, so that would be your percent experimental error, and the lower the error, the better. Okay, definitely another question I could ask you is how to read a vernier caliper. So you can go to that same simulation that we looked at in class when we did this particular lab, and remember how to read this. You're reading where the 0 is, right? So you have the 0, and you're reading where that is on the main scale. So in this case, it's past the 2.1. So this line right here would be 2.1. So it's 2.1 something. In eyeballing it, it looks kind of near the beginning, so it's probably 2.1, 2.11, 2.12, 2.13, something like that. To get that last digit exactly, I look on the vernier scale, right, the 0 through 9, and I ask myself which one of these lines, the 0, the 1, the 2, the 3, the 4, lines up best with any marking from above. And it turns out, if you look at this, sometimes it's hard to tell, but this case looks like the 3 lines up best. So you would read this as, this would be 2.13 centimeters. So that's how you'd read the vernier caliper. Okay? So you should practice. If you don't understand that, make sure you practice with that simulation. Okay, next. Make sure you know the difference between a vector quantity and a scalar quantity. So between a vector and a scalar. So a vector, right, has a magnitude and a direction. A scalar just has a magnitude. It doesn't have a direction. So some examples of like vectors and scalars, things like displacement. That would be a vector, right? Because it has a magnitude, so many meters or so many miles, whatever it is, and it has a direction, like northwest or at some degree, some angle. Velocity would be a vector. Force would be a vector. Acceleration would be a vector, etc. Okay, and then for scalars, I'll give you some examples. Things like, time has a magnitude, but it doesn't point in any physical direction, right? Mass has a magnitude, but no direction. Density. Distance would be like a scalar, because it doesn't matter, like when you say you're 4 miles from a particular point, it doesn't matter what direction, you're just given a magnitude, right? Et cetera, et cetera. Okay, so make sure you understand the difference between vectors and scalars. Okay, another thing that's important is when we did the lab on with the Kennen Force Platform, make sure you understand the relationship between the equilibrant and the resultant forces. So the whole idea was to add two force vectors together, right? Like let's say I have, we had the center ring, and then I had, say, F1 like this, and F2, say like this. And the idea was to add those together to find the resultant, right? Which maybe looks like this. But the way that we did that was we basically balanced those two forces with what's called the equilibrant, which was going in this direction. So this is the equilibrant force. And using that information, we want to find the resultant force, which is the R. So the R is our resultant force. Okay, so how do those two relate? Well, remember the magnitude of the resultant force. So ultimately we wanted that in newtons. That was equal to the magnitude of the equilibrant force. So whatever we had to put, right, remember we hung like, 230 grams, and we converted that to newtons. Well, that would be the same for the magnitude of the resultant force. It'd be whatever 230 grams is converted to newtons. And then the direction of the resultant force that was equal to the direction of the equilibrant force minus 180 degrees, right? Because it's the exact opposite direction. So it's going to be the direction of the equilibrant minus 180 degrees. So if you know, like if this is our x-axis and this is our y-axis, if you know this angle for the equilibrant, then you can subtract 180, and that will give you the angle for the resultant, which is the green one here. Right? You take the blue angle, subtract 180, and that'll give you what we want, which is the green angle. Okay, so that's important. You also want to be able to work with and interpret graphs. So let's say we have a position versus time graph that looks like this. So this is position let's say it's in meters versus time in seconds. And let's say the graph does this. Say it's constant at 1, then at 3 it's -2. Then let's say it's constant at -2 for 2 seconds, and then it goes to 0 at 6. So I could ask you a bunch of questions about this, right? I could say, like, what is the position at 4 seconds? Or I could say, what's the velocity at 1.5 seconds? And let's do another one. Let's say the velocity at 5.5 seconds. And then finally, maybe, where is the particle moving backwards? Over what time interval? Okay, so let's look at this. So position at 4 seconds. Well, that I can read directly off the graph, right? Because it's a position versus time graph. So if I go to 4 seconds, go down in the graph, I can read that value off. It's -2. So this is going to be equal to -2 meters. If I want to find the velocity at 1.5 seconds, well, 1.5 is right here. What does it mean to find the velocity? It means I have to find the slope, right, of the tangent line that just touches the graph at that point. So really it'd be the slope of this green tangent line. But because that slope is the same as this entire line, right, because it's like constant velocity, I can just find the slope of this entire line, and that will be the same as the slope of that tangent line. So the easiest way to do that is you could use the coordinates at the end, right? And we know that this coordinate is 1, 1. I know that this coordinate is 3, -2. So I could just calculate the slope based on that. Or even easier, you could use rise over run, right? If I start here, I need to go down 3, so my rise is -3, over 2, so my run is +2. So the slope must be -3 over 2, right, meters per second. So that would be my velocity. It's constant over that entire time interval, but I want to know specifically at 1.5, still -3/2, right, because it's constant over the entire time interval. What about the velocity at 5.5? Well, that would be this point, right, 5.5, so I go to the graph, I want to find this slope. Again, since it's constant from 5 to 6 seconds, I can just find the slope of that line. Well, in this case, my rise is +2, my run is +1, so this is going to be 2 over 1, which is 2 meters per second. And then when is the particle moving backwards? Well, it's going to be moving backwards when the velocity is negative. And how do I determine where the velocity is negative? That's where the slope is negative. So I guess from 1 to 3 seconds, that's where it's moving backwards, right? Here it's actually at rest, moving backwards. At rest again, here it's moving forwards because the slope is positive, right? The velocity tells you the direction. So I'm going to write this between 1 and 3, like interval notation. Okay, so definitely make sure you know how to do that. Also know how to interpret. So that was velocity versus time. Let's do a that was position versus time. Let's do a velocity versus time graph. So let's say this is velocity, meters per second, versus time in seconds. And let's say the graph looks like this. Okay, and I want to ask several questions about this. So let's say I want to know, based on that graph, what is the velocity at 1.5 seconds? I want to know the acceleration at 2.5 seconds. And I want to know the displacement from 1 to 5 seconds. Okay, so velocity at 1.5. Well, since this is a graph of velocity versus time, if I want to know the velocity at some particular time, I can just read the value from the graph, right? So I go to 1.5 seconds, go up to the graph, and then read it off. It looks like it's 2 meters per second. So this answer would be 2 meters per second. If I want to know the acceleration at 2.5, right, and I have a velocity versus time graph, I go to 2.5, go to the graph, and what am I calculating? If I want to know the acceleration, I'm calculating the slope, right? So this is going to be the slope of the line that just touches, the tangent line just touches the curve. But again, because the acceleration is constant over that entire time interval from 2 to 4 seconds, if I find the slope of that entire line, that must be the slope of my line right at 2.5 seconds. So how do I find that slope? Well, I would just use rise over run. So in this case, it's starting at 2, going down to -2. So the rise is a -4, and the run is a +2. Right, so this is going to be -4 over +2, but that equals -2, and it'll be meters per second squared. Okay, and then how do I find the displacement from 0 to 5 seconds? Well, remember when you have a velocity versus time graph, the displacement is the area underneath the graph. So probably what you would do is you would break this up into maybe a square here. Call this area 1, so I want to find that area. Then maybe this triangle, area 2. Then maybe this triangle, area 3. And you have to remember, when the velocity is positive, I have to add the areas, right? It'll be a positive displacement, and the velocity is negative. I have to subtract this area, so it'll be a negative displacement. So basically my displacement, my delta x, is going to be area 1 plus area 2 minus area 3. Well, area 1 is just a rectangle, right? So it's length times width. So this would be 2 meters per second times 2 seconds. That's going to be 4 meters. Area 2 is a triangle, so that's 1/2 base times height. So it'll be 1/2 times, I guess the base is 1, the height is 2. So that's going to be 1 meter. And in area 3 is another triangle, so 1/2 base times height. So it'll be 1/2 times, in this case, it looks like the base is 2, right? And the height is 2. So 2 times 2, and that's equal to 2 meters. So my displacement will be 4 plus 1 minus 2. So that'll be 3 meters. So from the starting position to the final position is 3 meters, right? Remember, displacement is final position minus initial position. So it's like x final minus x initial. In this case, it's 3 meters. And it's the area underneath the velocity versus time graph when you're computing it. Okay, the other thing, the other type of graphs you want to make sure you know how to interpret are the position versus time, velocity versus time, and acceleration versus time graphs that we did when we we're analyzing the movies, right? When we threw up the ball or dropped the ball, or analyze me jumping when I was doing the vertical jump. So make sure you know how to analyze those. So I'll give you an example. Let's say I'll do the one where we throw the ball up. So throw a ball straight upward. And remember, when we looked at position versus time, the graph was something like this, right? It started at some height, and it kind of peaked, and then went down to 0. Then when we did velocity versus time, so this is meters per second, it was the slope of the previous graph, right? So in this case, the velocity, the slope here is positive, right? So the velocity was positive. Then it's like less positive, less positive, less positive. At the peak, it's 0. It's 0. And it becomes negative, more negative. So it's going to look like this. Actually, let me see the first one's like that. So something like that. And then the acceleration is the slope of the velocity versus time graph. So this is acceleration, meters per second squared. And since that slope is constant and negative, then the acceleration was like a constant negative value. And in theory, right, if there's no air resistance, this value should be negative 9.8 meters per second squared. Okay, so I probably will give you an example where I just have you like estimate values. Like, if I say, what is the position of the ball at the peak height, then you could like, you could estimate this by like reading off the value here, right, from the peak height and so on and so forth. So you just want to make sure you understand those particular graphs. Okay, another thing that you should be familiar with is in projectile motion, let's say you're given a launch velocity, right, of the projectile. So it's a vector. I'm going to call it V naught. And you're given the fact that the magnitude is 185 meters per second. And the launch angle is, say, 60 degrees. And you want to find the two components. You want to find the x component of the launch velocity and the y component. So what you have to do is you have to project this, right, onto the x-axis. This would be like v naught x. If I project this onto the y-axis, the vector on the y, this will be v naught y. And then if I extract this right triangle, right, that contains the reference angle here, then that will allow me to figure out v naught x and v naught y, right? If I extract this right triangle, the magnitude, the hypotenuse, is my 185. This, of course, is 60 degrees. This is v naught x, and then this side is the same as v naught y. So if you want to find v naught x, it's going to involve, since it's adjacent in your hypotenuse, it's going to involve cosine, right? So v naught x is going to be 185 times cosine of 60 degrees, and that turns out to be 92.5 meters per second. And then v naught y is going to be 185 times sine of 60, and that will end up being 160.2 meters per second. So make sure you know how to do that. Make sure you know how to find the components, right, of a vector. Another thing with projectile motion is I could give you the launch speed, which is like the magnitude of launch velocity, and I could ask for the range, right? So, for example, let me draw this out. Let's say this is the launch velocity again, right? V naught. And let's say, again, this is 60 degrees. and I tell you that this V naught is 139 meters per second. So that's like the launch speed, right? It's the magnitude of launch velocity. Now we know what's going to happen, right? This projectile is going to like rise to a peak and then come back down and hit the ground here. And since this takeoff height is the same as the landing height, then this horizontal displacement is called the range. So I could ask you to calculate the range. Well, the easiest way to do this is there's a formula for range, where range is equal to V naught squared times sine of 2 theta divided by g. And you want to just make sure you use the right units. So in this case, since I have the velocity is meters per second, we're just in SI units. So you would just plug in, right? This would be like 139 squared times sine of 2 times 60, so that's 120, divided by, and in G, in SI units is 9.8. And in this case, you would get something like 1707.4 meters, right? So that's a matter of just plugging it in. Okay, Newton's second law. What if I give you a problem like this, where you have a mass, so some object, right, it has a mass m, you apply a force to it, so there's an applied force to the right, and let's say there's friction, so it's moving, so there's going to be like a kinetic frictional force acting to the left. And let's say you're given this information, you're given the mass is 100 kilograms. You're given the magnitude of the applied force is, say, 500 newtons. And you're given, say, that the coefficient of kinetic friction is 0.4. Remember, coefficients are unitless, right? There's no unit, so it's just 0.4, it's just a number. And let's say we want to find what is Fk, and then what is the acceleration of that particular object. Okay, so to figure out Fk, remember Fk is equal to mu k times n, where n is the normal force. Well, in this case, right, if I isolate my object, we have 4 forces acting, right? I have the applied force acting to the right. I have a kinetic frictional force acting to the left. I have the weight of the object acting down. So this is like mg. And I have a normal force that the table exerts up on the object. So to figure out the normal force, I basically have to use Newton's second law in the y direction. Okay, so it's equal to MAY. But since it's not moving, right, it's not moving off the table, the acceleration in the y direction is 0. So basically the sum of the forces in the y direction is equal to 0. Well, the only forces acting in the y direction are the normal force, and it's positive, and the weight, and it's negative, so minus mg, that's going to equal 0. So this basically tells us that the normal force is equal to the weight. Okay, and we know m is 100 kilograms. We know G 9.8, so this is just 980 newtons. So now I can figure out the kinetic frictional force, right? It's going to be 0.4 times 980. And that turns out to be 392 newtons. Okay, now I want to figure out the acceleration. So now I apply Newton's second law to the x direction. So sum of the forces in the x equals max. Well, what are the forces acting in the x direction? I have Fa, which is positive, and then minus Fk, because it's negative, equals max. Well, Fa is 500, Fk is 392, and that's got to equal 100 times ax, right? The mass is 100. I'm looking for ax. So this is simply going to be, this is basically 108, right, is equal to 100 ax. And if I divide by 100, then that cancels. I'm going to get ax is equal to 1.08 meters per second squared. So that would be my acceleration. So I'm just using Newton's second law, right, in the x direction. Okay. Another way I could ask a Newton's second law question is given the setup that we had in lab, where we had the cart, right, on the air track. Remember that was mass 1. Then we had like a pulley, and then the cart was connected by a string, right, over the pulley, and then we had a suspended mass, M2. So I could ask, what is the acceleration of that system? And then what is the tension in the string? So let's say we want to find the acceleration, and then T, which is the tension in the string. Well, you don't have to really apply Newton's second law. We already derived the formulas for this, so you can just use those formulas. Right? Remember, the acceleration was simply m2 times g over m1 plus m2. Right? We derived that formula. And since we're in CGS units now, right, grams, you have to be careful. This is going to be, let's say we have to know these masses, right? Let's say we're given that m1, the mass of the cart, is 180 grams, and then m2 is 20 grams. Okay, so again, we're in CGS units. So if I plug in, M2 is 20. Because we're in CGS units, that means G is going to be 980. And then I'm going to divide by 180 plus 20. Make sure you do that correctly in your calculator, right? You're dividing by that whole sum. And what you should find is this equals 98 centimeters per second squared. So that's the acceleration of the system. And then to find the tension, there's actually two ways you could do it. You could use the mass of the cart, and that formula would just be m1 times a, right? Or we could use the suspended mass, and remember that formula was something like, because it was m2 times g minus a. Either way will work. So in this case, we could say it's 180 times 98. That will give us 17,640. Remember, the units for force in CGS are dynes. Or if I did it this way, it would be 20 times 980 minus 98. And that ends up being the same thing, right? 17,640 dynes. So either way, you could be asked to find the acceleration and then the tension. Okay, an example involving friction. Let's say I give you a graph of the frictional force when I was pulling that wooden cart. Right, so let's say the graph looks like this. So it's going to be force in newtons versus time in seconds. And let's say, so it kind of like goes up, it kind of peaks. Then the cart starts moving, kind of plateaus, and when I stop pulling, it goes down to 0. Let's say you're told that the mass of the cart was 0.72 kilograms, like the total mass, and we want to find μs and μk. We want to find the two coefficients, right, given that information. So remember, to find the coefficients, μs is simply going to be Fs max divided by the normal force. And then μk will be Fk divided by the normal force. So how do I find the normal force? Well, if in the cart, right, in the vertical direction, I only have two forces acting. I have the weight acting down, which is mg, and I have the normal force acting up. So if you apply Newton's second law to the y direction, it's equal to may, which is 0 in this case. It's going to be normal force minus the weight is equal to 0. So again, because it's on a flat surface, the normal force is just equal to the weight. So we know the mass, that's 0.72. We know g, 9.8. So if you worked it out, it turns out it's going to be 7.056 newtons. Okay, so I know the denominators, right, for each of these. So these are both going to be 7.056. How do I find the numerators? How do I find Fs max and Fk? That's when you use the graph. So you're going to have to estimate. Like, remember, Fs max should be the highest point here, this peak. So you're going to estimate by reading off that value. Like, this should be Fs max, where that value is. Let's say it's like 4.1, just for illustration. So then this value would be 4.1. And then Fk is going to be like the plateau, the average of the plateau. So you kind of like average it and read off that value, Fk. Let's say in this case it's 3.6. So this would be 3.6. And then you can finish calculating these. So mu-s in this particular example will be 0.58, and in mu-k would be 0.51. Okay, so using that graph, you're able to find Fs max and Fk, and then that will allow you to calculate mu-s and mu-k once you know the normal force. All right, there'll be some stuff with torque. Let me give you guys one torque example. Let's say I have like a seesaw board, and I have a knife edge right in the center, right? And I'm going to consider this to be my axis of rotation at that same spot. And then let's say I have several masses. So let's say I have mass 1, mass 2, and then mass 3. And I know these distances. Let's say this distance is 0.5 meters. Let's say from here to the rotation point is 1 meter. And let's say from here to rotation point is 1.5 meters. Let's say we're given M1 is 10 kilograms. We're given M2 is 20 kilograms. And we want to find M3. So M3 is unknown. Okay, so think about what's going on here, right? I have actually on that beam, the seesaw, I have 5 forces acting. So let me draw this again. So 5 forces acting. I have weight 1 acting where M1 is, right? And remember, the weight is going to be M1g. That's my force. And I know that this distance, L1, is 0.5 meters. Then I have weight 2, which is M2g. And that distance is L2, but that's 1 meter. This one is 0.5 meters. And then I have weight 3, which is M3g. And this distance is L3, which is 1.5 meters. Then I also have the weight of the entire seesaw itself acting at the center of mass. I'll just call that W, which is mg. And I have a normal force pushing up, that the knife edge, the stand, is pushing up on the seesaw at that center. So I have 5 forces because we're assuming this is in rotational equilibrium, right? Assume it's in rotational equilibrium. So that means the sum of the torques about this point, I'm considering this max rotation right in the center there, has to equal 0. So I have 5 forces, I'm going to have 5 torques, right? So I have a torque due to weight 1, plus a torque due to weight 2, plus a torque due to weight 3, plus a torque due to the weight of the seesaw itself, plus a torque due to normal force equals 0. And because both the normal force and the weight of the seesaw pass right through the axis of rotation, they don't have a moment arm, right? So they're not going to contribute a torque. So these two values are 0. The torque due to the weight of the seesaw and torque due to normal force are 0. And then the other ones I can compute. Remember, in general, a torque is plus or minus the force times the moment arm. So the torque due to weight 1 is going to be the force, which is the weight, right? And that was, so it's really the mass times 9.8. That's our force. And then the moment arm was the perpendicular distance from the line of action of the force to the actual rotation, but that's just L1 here, right? That's 0.5. And then if I imagine that W1 is the only force acting, how would it rotate the balance beam, the seesaw, about the point of rotation? It would rotate it counterclockwise, right? So that's going to be a positive torque. Okay, then I have the torque due to weight 2. Well, the weight 2 is going to be 20 times 9.8 times the moment arm. The moment arm is 1 meter. And that torque is also positive. And then the torque due to weight, this should be weight 3. Weight 3 is going to be the mass 3, which I don't know, so I'll leave that open, times 9.8 times the moment arm, but the moment arm is just this horizontal distance, 1.5 meters. And since that weight, right, if I actually applied W3 there, it would cause it to rotate clockwise. This is a negative torque, and that's going to equal 0. So now you can solve this equation for M3. Basically, you're going to find M3 is equal to this whole thing divided by, so I can bring this term to the right-hand side, and then I'll divide by 9.8 times 1.5. And that'll give me mass 3, which in this case, it ends up equaling 16.7 kilograms. Okay, so you'll definitely get some torque problems. You want to make sure you understand how to solve torque problems. All right. Another thing that could appear on the exam is how to compute percent experimental accuracy. So let me do an example of that. So remember the formula for percent experimental accuracy, it's equal to the average absolute deviation divided by the average value times 100. Right, and that'll make it a percent. So if I give you some data, let's say we measured the height of an object in centimeters, and let's say we measured it 5 times, and we got these values: 3.52, 3.52, 3.46, 3.42, 3.52. So remember, the first thing you have to do is you have to average those 5 values, right? If you average them, you're going to get 3.488. But we have to round everything to the resolution of the instrument. And because each of these values, right, has 2 decimal places, the resolution of this instrument is 0.01, right, centimeters. So basically, I want to round this 2 places, so 2 decimal places. So this would be 3.49, right? That would be my average height. Okay, then I have a second column of my absolute deviations, also in centimeters. And remember, to find these are how far each data value is away from the mean. So mathematically, what you're doing is you're taking each data value and you're subtracting the mean, subtracting your average, and then taking the absolute value of that. So 3.52 minus 3.49 is 0.03, and an absolute value of that is 0.03, right? So, and then a lot of these you can do in your head, right? You can just say, well, how far away is that from my average? Then this from my average. And you're going to find that these are going to be, this one is 0.03. Let's see, this one is 0.03 as well. It's below, but remember it's absolute value. Then this is 0.07, and this is 0.03. Okay, Then I average my absolute deviations. If you average these, you're going to get 0.038. But you have to remember to round to the resolution of the instrument, which is 2 decimal places. So this would be 0.04. This is your average absolute deviation, right? That 0.04. So now the final step to find percent experimental accuracy is I take my average absolute deviation, 0.04, divide by my average height, 3.49, times 100. In this case, I'll end up getting 1.146%. And remember, the lower the better. It means this is really a measure of the variability, right? So the lower the percent experimental accuracy means you have less variability. Those 5 values are pretty close to one another. Another thing I could do is I could give you mass and volume, right, 2 values, and say calculate density. Well, that's simply going to be, remember, density is usually rho, it's going to be the mass divided by the volume. But then I could also ask you to calculate the percent experimental accuracy for density. And remember, that depends on the formula, right? Because the formula involved dividing 2 quantities. Whenever you have a formula that involves multiplying or dividing quantities, either multiplying or dividing, if you want to find the percent experimental accuracy of this dependent variable, in this case of the density, then the rule is you have to add these respective percent accuracies. So in this case, it would be the percent experimental accuracy for mass plus the percent experimental accuracy for volume. If you add those two together, that will give you the percent experimental accuracy for density in this case. Make sure so we did that one experiment on the air track, right, where we had a flag length. Let's say I give you, the flag length was 30 centimeters, and it's on a flat air track, and let's say the time that it took the flag to pass through the photo gate was, 0.05 seconds. I could ask you to find the velocity, right? The average velocity. If it's flat, it's really going to be the constant velocity of that cart. Well, to do that, all you need to do, right? Velocity is really delta x over delta t. So the delta x really is our flag length. So there'd be 30 centimeters divided by 0.05 seconds. And you would work that out. And that, I think it's like 600, but let me double check this. So 30 divided by 0.05. Yeah, this is going to be 600 centimeters per second. Okay, so if it's on a flat air track, to calculate the constant velocity, it's simply going to be the flag length divided by the time that it took the time that the flag took to pass through the photo gate. And then the other possibility was, remember when we had an incline air track? So when it was on the incline, we started the car at rest right before it triggered the photo gate. So let's say this is the photo gate right here. And we wanted to find the final velocity, right, of the cart as the end of the cart passed through. And remember that formula, I'll just give it to you. So the final velocity, V final, that was twice delta x over delta t. So it's twice the flag length divided by the time, if you want to know the final velocity. If it starts at rest, it accelerates down with constant acceleration, then the final velocity is twice the average velocity. Let's see, what else might appear on the exam? Oh, if you're adding vectors graphically, right, remember how to add them tip to tail. Like if I have say v1 and, I don't know, v2. If I want to find, I'll call it R, which is v1 plus v2, then I could do this graphically, right? You could start with v1. Usually what you do is you have some type of coordinate system. So I move the tail of v1 to the origin of the coordinate system, right? Maintaining the same direction. So let's say this is v1. Then I move the tail of v2 to the tip of v1. Again, maintaining the same length, same orientation, same direction. So it'll be something like this. And then if I draw a vector from, so this is my v2. So now to add them, I draw a vector from the tail of the first, so the tail of v1 from the origin, to the tip of the second one, right? Or the last one if you're adding multiple vectors. So this would be my v1 plus v2. So that's R in this case. That's v1 plus v2. All right, so just know general how to add vectors like tip to tail. Okay, great. So hopefully you'll have a chance. So the last 2 full weeks of classes, we will review this. I'll go over this. This video is mostly for the students who, for some reason, can't make it to class, and at least you'll have this video to look at. Great. Thank you.